Heldmann, who's going to talk to us about the future of field research campaigns. In other words, what we're doing in the meantime until we decide to go back, right?
Well, thanks everyone for coming today and for sticking through to the end of the forum. And that is a very tough act to follow. I do not have a video. I do not have beautiful music. I have slides and myself. I can't dance, no. But what I'd like to do is take this opportunity just to talk about some of the work that's being done currently as we make our way back to the moon and onto Mars, et cetera. And Yvonne and Greg asked me to talk about the future of field campaign research. So what I'd like to do is talk about some of my own thoughts on what's happening now and why we're doing this and what we're getting out of it and where things might go in the future. And there's a lot of field work that goes on all across NASA, outside of NASA with various groups. And I'm just going to highlight some of the things that are going on within CERVI because this is the CERVI Exploration Science Forum. And I'm just going to put this disclaimer in the front in case you're wondering if I'm pro field campaigns or not, that I'm leading the finesse team out of CERVI, which is focused on doing field research to study impacts in volcanism for science and exploration purposes. So just get that out of the way. So really, why do we do this? And what are the main tenets of field campaign research? And there's been a lot of thought by a lot of people that have listed some ideas on this topic. And there's really four functions, and Pascal Lee has done a lot of work to try and outline these as well. One thing that field campaigns can do is help you learn and do comparison studies. There have been multiple talks in this forum this week. These are images that Brent Gary presented earlier at the forum. Looking at various volcanic features on the Earth and on the Moon and doing comparison studies and trying to understand how these features form, what are their characteristics, how do they evolve, and doing this boots on the ground, making the measurements, and then comparing that with, for example, the remote sensing data that we have from the Moon, trying to understand comparative planetology, essentially, doing the science. Another thing you can do is test. You can test hardware, hypotheses, strategies, etc. And it's a pretty low cost, low risk way to test these things before we actually fly them. So here's Kelsey Young. She's on Tim Glatch's RISE team out in the field. She's come out in the field with us as well. That's one of the things about CERVI is that it's very cross-disciplinary and cross-team, both within the teams and out in the broader community as well. So we can test things, we can take them out in the field and see if they work, and we can break them, and then we can fix them, and then we can make them better, and then we can go back and test them again. And that way that's feed forward into the future mission architecture so that we can have the best missions going forward. Another thing you can do is train. You can train crews, ground personnel, students, etc. It's a really great proving ground, and so you can run through the paces, you can train folks how to use the hardware, how to use the software, how to interact together, how the teams actually function, how data flows, how communication actually happens, all those things you need to do to make sure that your mission's a success. And you can do it over and over and over again. And also the fourth one is engage. Engage with international partners, engage within our own community, engage with the public, engage with students. And there are a lot of programs right now that are out there to do that. And so if there are people that are interested in getting involved with NASA research, getting involved in planetary science and exploration, there are ways to do that. So, for example, you heard a talk earlier. Jake Bleacher is working with Dave Kring, leading the Zuni Bandera Volcanic Field Camp that's coming up. That's out of Kring's CERVI team. We're doing a program through our team called Spaceward Bound, where we bring students and teachers out into the field. The RISE team is bringing students and journalism students out into the field so that they can learn how to actually cover science and write stories and get the word out there. So the idea is we can actually bring these folks in, and I'm very eager to do that, and I do it a lot. And I think it's a great experience, especially when you bring, students and teachers out into the field and they just get so much out of it and bring it back to their classrooms and help, we were just talking about how do we spread the word and show folks what we need to do, get more people on board. So I'll just point out that, this is not new per se. It's not groundbreaking, and it's really fun. I had actually spent far too much time just trolling through the web and looking at all the images from the previous Apollo training sessions. And I really tried to find a picture of Jim Head, and I couldn't find one. I wanted to put that in there. But here are Apollo 13 astronauts studying lava flows out in Hawaii, which are things that many of us in this room do. Gordon Swan testing field procedures in these pressurized suits. So this may look familiar. There's been a lot of work that's been going on in the past few years trying to do the same type of work for the return to the moon and going on to Mars. I like this one too, Apollo 15 driving the lunar roving vehicle out in the desert. We're testing these capabilities, and we did it before. We have to remind ourselves that it's a logical thing to do. You test these things out in the field before you actually fly them to these other planetary destinations. So this is not a new thing. This has been going on for decades. And what's new is that now we're tailoring it to the missions that we see coming up on the horizon and trying to make the field testing and the field campaigns most relevant to the future mission opportunities. Now, there's a few different kinds of field campaigns as I see it. There are science-focused expeditions, where there's a lot of work that's funded to go and do pure science and to learn about that field site and do some comparative planetology and learn about planetary bodies in the solar system. And that's wonderful. And we can go to lots of different places and we can do that. There's also exploration-focused expeditions. So here is a bare bones MSL lander before going to Mars, trying to figure out how are we going to drive this thing in sand dunes, for example. So this is an engineering type of test, trying to make sure that this exploration actually works. What I want to focus on are science campaigns that are infused with the exploration, so where you actually do both. You have a science and exploration-based field research program to generate the strategic knowledge that we need to prepare for human and robotic exploration of the solar system. And I think that's really where the convergence of this work comes together so that we can get the science out of these future missions and make sure that we move forward in the most productive way. And so we've heard over and over for many, many years, and also on the first morning of the forum, science enables exploration and exploration enables science. And that's really the philosophy behind what we're trying to do here. And I'll also point out for the current work, at least the things that I'm involved with, and I know a lot of folks here are involved with, it's an emphasis on the near-term return on technology development and operational trades. What do we need to do now in order to inform our future missions, and how can we actually make changes in those mission architectures based on what we're learning? Because ultimately that's the whole goal, right? We're doing these tests so that we can make missions better. So have we been able to do that? So I'll just give you one example where I think it actually has worked, and it's relevant here because this is relevant to the Resource Prospector mission, which is a Lunar Polar Rover mission. It's in Phase A, funded out of NASA's Human Exploration Operations Mission Directorate, to follow up on the lunar polar volatile story, to actually drive a rover and map out the extent of the volatiles and actually do assays and do drilling and get down and actually identify where it is on a smaller scale than we're able to do from orbit. And if you'd like to learn more about RP, of course, there's a whole community workshop tomorrow in this room. So anyone's welcome to attend that. You'll learn a whole lot about RP. If you can't attend, it will be broadcast on the web, just like the forum is, and also the talks will be archived, so you can learn more about it then. The agenda's online. So RP will locate the near-surface volatiles, excavate and analyze those samples, and then have ISRU, or in situ resource utilization, implications for can we actually extract them, can we use them, can we demonstrate that we can do it. So we had a field campaign last year called the Mojave Volatiles Prospector, MVP. This was funded out of NASA's Planetary Science Division, where we took a rover, the Ames KRX rover right there, into the desert to do some testing and did a full-up mission simulation in the style of what RP would be, or any sort of mission that has near real-time operations with a rover where you're out prospecting and trying to map out something of interest, in this case water. So you have a science operations center, as you will with RP or any other mission like that. There's a rover operations center, sort of a front room type of thing, which you would have with RP or some other type of mission. And then you have a whole ground data systems support mechanism that's in place. So this, folks that have been doing a lot of field work will probably recognize this XGDS. This is led by the Intelligent Robotics Group here at Ames. And so this is just an example, one of many examples of the capabilities that you have here, where you're looking at the actual rover traverse here in red, and it's basically painting out neutron counts. So this is the neutron spectrometer data. And you can see you come over here and you've got a big hotspot here, so there's something of interest there which maybe you want to follow up on. And it gives you a nice view from a geographic perspective of looking at the data to see where your hotspots are and where the areas of interest are, because you have to make decisions sort of on the fly and in real time and decide, oh, this is somewhere I want to stop, or no, keep going. And you don't have time to spend days or months or years analyzing the data as we like to do in science. So it's been a really great learning experience to actually do these field campaigns, knowing we have to get the science out, knowing we have to get the data back in order to write the papers, and figuring out what tools do we actually need and working the science and the engineering together. So just what do you get out of these types of things? I just want to give you a few concrete examples of how, in this case, we can inform the RP mission and say, hey, these are some of the things that we might need to include in the mission For example, instrument maturation, so increasing the TRL of the prospecting instruments. So you've heard talks about NERVIS and NERVIS testing, that's the near-infrared spectrometer, and the neutron spectrometer. Those are the two prospecting instruments on RP. So we put them on the rover and we drove them in the desert. We showed that with their instrument performance and the operational architecture surrounding that, you can actually detect water at lunar abundances way out in the desert where you've got 5 weight percent or less water, that it actually works and you can do it. As I mentioned before, the ground data systems development, identify, produce, and test specific real-time analysis tools and displays. It is not a trivial thing to try and think ahead about what you're actually going to need when you're sitting at that console position, needing to look at that data because you have to make a decision, what the rover is going to do next. So we develop various ways of displaying the data, and then develop some modifications that you need to have in place. You have to be able to change where you want the rover to go in real time. You have to be able to change that traverse path of the rover, get it uploaded and get it executed, in a matter of 10 minutes or less. You don't have a day to do it like you do on Mars or, longer durations for other planetary destinations. And so how you do that activity planning in near real time. And so you need specific ground data systems to help you do that. And then also looking at mission architecture in the operations consoles and who has responsibility for what, and what are those console positions? Who do you need sitting in that science operations center, and who do you need sitting in that front room? Well, we figured out through some field testing that you need a real-time science position, which we call RT-Sci. You need someone there who is able to make those calls and is looking at the data in real time to decide, okay, should the rover keep going? Should it stop? Should it go back? Should it drill? Etc. And we also found it was very useful and essential to have the real-time science person in direct communication with the rover navigation people. Go over here, here's where the interesting area is, and avoid that rock, and then there's a lot of back and forth with the navigation folks and the science folks to actually optimize the traverse path and get the data back that we need in a safe manner that's consistent with the engineering constraints. And also decision-making authority. The scientists actually have to have some decision-making authority in real time, which is a little bit scary. But if you see the hot spot that you saw the neutron counts and you say, that's an interesting spot, we need to stop there. And the scientists make that call because they are the ones with the training and the knowledge and the expertise to understand what's happening scientifically and in the whole context of what's going on in that region. And they have to be able to make that call because otherwise you keep going and you've already passed that point. So within CERBI and peripherally, there's a lot of science and exploration going on. I mentioned a few of the teams, the Finesse team, Tim's Rise team, Dave Kring's Lunar team, and then Darlene Lim is leading sort of our sister team. We're teamed together on a basalt project, which is studying volcanic terrains and biology. And the idea of all of these types of activities, and there are a whole lot more that I can't even list, but to do the planetary science and then do the exploration. So looking at the concepts of operation and looking at the capabilities that you need to actually do the science. So for some specific examples of what you can look at in terms of capabilities, these are some of the topics of consideration that we're testing in the field, and many groups are. I won't go into each of them in detail, but the idea of a habitat intravehicular workstation, sort of a little mini lab that you have out in the field so that you can do some real quick and dirty analyses and kind of decide, okay, which samples do we need, or do we need to go back out and get more data while we're right here, and how does this actually work? And it turns out the IV workstation is an incredibly important part of a field campaign and doing the field work. Mobile instrument platforms, so you have some robotic asset that can come with you. It can carry gear, it can carry samples, it can provide capabilities like comm, et cetera, et cetera. The backpacks, what you need in your EVA systems and your suits. Distributed science backroom teams, because you probably, over the long duration, won't have everyone co-located in the same room, but you're going to have people in various areas, and it's non-trivial to figure out how you have that data flow going, how you have that communication going, how you have the decision-making authority working, all of those types of issues, and you can just test them by doing these field tests. And then there's also the ground data systems. I mentioned XGDS. There's Playbook, which is a scheduling tool, and getting those all integrated. So there are all these various components that you can actually test out in the field. This is, you heard a talk earlier today. Jake Bleacher was talking about this and provided this slide to identify the importance of portable field instruments, because we're going to get new science out, we're going to get data, but you need to figure out what are the right instruments that you need in the field and how good do they have to be. So what are the tools that you actually need? So by going out into the field and doing some of the science, you can actually start assessing this from a quantitative perspective. You know, what's the quality of data you got out? How long did it take the person to actually use that? You know, and how does that parlay into your science results at the end of the day? And try and figure out, all right, what is the optimal suite of tools that you would need someone to bring in order to achieve your science objectives. So this is work that's still ongoing. There's also human factors work that's going on as well. This is a paper that Barbara Cohen led, and it's a focus on astronaut training, where up at a very remote impact crater in northern Canada, had astronauts out there and had a science team out there, and figuring out, okay, what do we actually need to teach people when they go out into the field to make sure that they collect the right samples, in this case for doing age dating of an impact crater. Because you can't just get any sample, you need to pick the right ones. And how do you actually do it? And what information do they need before they go out there? How can they interact with the science backroom? And I invite you to read the paper. It's in the Journal of Human Performance in Extreme Environments. It's very interesting. So we can do all these types of things, and that's great. And it gets back down to risk reduction, right? And there are some risks that have been identified within the Human Exploration Operations Mission Directorate, and focusing here on what we call human and automation robotic integration. And so there are discipline scientists for various activities that are going on. Jessica Marquez is the discipline scientist here, and she provided this slide. So what they're interested in are looking at things like communication time delays. Well, we do that in the field because we can build in time delays between what's happening in the field and that science backroom. Teleoperations and autonomous commanding of your robotic agents. Well, we can do that too because we bring rovers out into the field and you can command them in different manners and see how that actually works when you're trying to achieve your science objectives. How do you supervise these complex vehicles? What different mixed agents do you actually use? What are the robotic assets you actually need? Human-robot team coordination, crew autonomy, how much do they need to be told? How much can you just let them go? What training goes behind that? So all of these types of things we can address by doing this work in the field. I'm going to skip these, but they're on the web for your own reference. Those are just looking at the Human Research Project and all the things that we're doing that are relevant to that as well in terms of risk reduction. But what I want to get to is what I was supposed to talk about the whole time, which is the future. Science enabling exploration and exploration enabling science. So here are some thoughts that are my own and not necessarily the thoughts of NASA. So in the future, I'm thinking, well, hopefully we have a lunar base. I think we've talked about that a lot this week. And in my mind, we should just be routinely going to that lunar base and doing research and doing science. And it's sort of the Antarctica model, where right now folks routinely go down every season. Sometimes you winter over. And you go down and you do your research and you come back and logistics are provided and you do your science and you come home. And it's a great place for graduate students and scientists and engineers to work. So hopefully we will have something like that on the moon where people would just routinely go and that's where they would do their research. And why might you do that? Well, there's a few reasons. And there's more detail. Chris McKay published a paper a few years ago on this topic, which has a lot of additional good thoughts. But here are just some high-level reasons why you might want to have this lunar base. Maintain international influence. Right? In Antarctica, many countries have their own bases down in Antarctica for various political reasons. We may want to have that on the moon as well. Pave the way for other applications. So for example, in Antarctica, there's a big tourism industry, and you can go and you take a cruise around there if you don't want to, slum it with the scientists. You can go and have a very nice experience. So that's something that, could potentially happen on the moon as well, where there are other industries and applications that would open up once we forge ahead on that frontier. Learn more about the moon, do the science. We've heard talks all week about what we know about the moon and even more what we don't know. So by going there and getting there, and James' talk just before this was a great example of that. Assess the health impacts of living in space. There are a lot of things that we don't know. Take a look at the Human Research Project if you would like to know the specific things that we still need to understand before we can do really long-term settlement. Learn to build and operate an extraterrestrial base. The moon is a really good place to do that. It's only a few days away. So I think I'm preaching to the choir and I don't need to make that case here. But in order to go out into the solar system, perhaps we can start at the moon and move out from there. And also become an interplanetary species so that we're not confined to Earth forever. It won't work forever, so we need to go somewhere else. And so by having a moon, this may be one good place to actually start that journey. So how are we going to get there? So how do we get from here to there? Well, we have field campaigns in the meantime, and that's great. And we'll do a lot of good work with that. But how can we make sure we keep that going? Yeah, this is just going to other places. So I was having lunch with Noah Petro the other day, and we were talking about this talk and fieldwork in general. And he said, what would Cervican 22 look like? And I was like, that's a good question. I'm going to think about that, and I'm going to come up with some things. So for Yvonne and Greg, or whoever is running Cervi or its equivalent in several decades, I would like to provide some example text that may be put into the call for proposals in a few years. So by then, please, I hope that we can be saying field work on the moon and at asteroids by both humans and robots is encouraged. We should be supporting that work at that point. Proposed research should include both scientific and exploration-driven activities. So we're going to be still maintaining that same philosophy on that same path to get us out into space. Proposers are encouraged to make use of the lunar base, obviously, that's there, and the research station that has been established on the moon. You can do sorties from this site, are encouraged to fulfill your science and your exploration objectives. So go elsewhere on the moon, go off the moon, wherever you need to go to get your science done. You must include a lunar-based logistics request with your proposal. So that's similar to what you have to include now for Antarctica. Tell us where you want to go, tell us where you need flights, tell us how long you're going to stay, and we'll take care of the rest. And as the perspective from a PI, I'm going to include this too. Transport to and from the moon is at no cost to the PI. NASA will cover it, or whatever entity. It's similar to how Antarctica works, right? You decide you're going to go and NSF pays for your logistics. And logistics service will be provided by NASA or whatever government agency or other institution. So hopefully by then we're actually doing work on the moon, and we're doing the things that we've been talking about this entire week because we have a very great foundation for what we need to do, and I think good justification for why we need to do it. And now we just have to continue down the path of trying to work and make sure that the programs and the support are in place to make this happen. So with that, I think I'm probably, yeah, over time.
Any questions or discussions for Jen? I see one coming.
Just on the general topic.
Please state your name.
My name is Nathan Schwadron, University of New Hampshire. There's been a lot of discussion throughout this meeting about how we get back to the moon, and international collaboration comes up time and time again. I'm sort of struck by looking at this group and what's been achieved here at ESF, that we have in the scientific community actually achieved an international community that's helped us achieve some of the aspects of the peaceful types of exploration in the future. I would argue that this is precisely the model that we need for